Good evening. In this tutorial, we are going to look at how to run regression analysis in Excel. So to run regression analysis in Excel, what we need to make sure is that we have the data already in our Excel sheet, like I have used this data as an example. So now what we are going to do is to see that we have the option which we call analyze, which should be one of the tabs here. And to have it, it means we have got to first make sure that it is displaying here in our Excel sheet. So to make sure that we have an analyze button, we are going to, possibly you have the analyze button already. Is it this?
If you go to data,
Let me see this.
analyze or data analysis.
Yes. So yes, to add the analyze option here, I'm coming at files here. Then options.
But if you go to data, analysis.
Yes, if it is not there when you click where there is data, that you don't have the word analyze, you can add it as an add-in here. Add-in. Add-ins, go, analyze, should be ticked on here. Then we can say okay.
But where is it now?
Pardon, Wilber. I've missed.
We want to have the word analyze, this one.
But I don't make it here.
Analyze
Data
here.
analysis.
If you are not seeing it, because we are not seeing the word data analysis here, for you to see it, that you have it, you go under data. Just in the ribbon that has home, insert, there's data there. There should be an option where you're seeing the word data analysis. If you have it already, then you don't need to insert it.
You have it?
Yes? Yeah, you already have it. Yeah, yeah. Windows.
Okay.
Okay. So now we are going to use this option, data analysis. You click it. Data analysis, there are two ways. Do you want to run correlation? Do you want to learn what do we want to run? Or regression? But now I'm scrolling down to look for regression. This one. Then we say okay. Yes. So our regression, what do we want to be our independent variable? Independent variables and the dependent variables. So let me see. Risk score. Let us have risk score as our work here, which is the dependent variable. What do we want to be our dependent variable? I'm selecting risk scores. Then the independent variables, I'm selecting these three. But to select the three, you highlight all of them. I'm highlighting all the three. Okay. Have we highlighted?
We're doing Y as risk score, then X as well.
X, we are selecting all the three: age, blood pressure, and cholesterol levels.
The three of them. Okay.
The three of them, you highlight the three of them at once. Let us include the labels, right? Our confidence level, let us maintain our confidence level to be 95%. Because when we are 95% confident, it means that we are allowing 5% error.
5% error.
5% error, then you are 95% confident. The 5% error is what we are calling the 0.05%. That's 5 out of 100. So the more confident you be, the less the error. If you're 99% confident, then you're 1% you're expecting 1% error, which is 0.01. So now we are leaving it to be 95 because that's the allowable minimum confidence level. Now output here, we are going to say that our output range, where do we want our output to be? Output range tells us where do we want our data to be. Let the regression be there. To me, I'm selecting here as F1. Let that regression start from there. So these other values, residual values, these ones we may leave them for now, but let us use normal probability plots. Normal probability plots. Yeah. So that normal probability plot is activated. Then we can say okay. Okay. So when we get that done there, for me, my screen is a little smaller, but I want to, okay. Oh. Okay. My screen is still struggling here, but I can as well lift off that. And then
The result is not same.
And over, and then we have this probability output. Why we don't have probability output? Wilber? You have what?
The result is not clear.
probability أنا اللي حاجات دي بعدين كويسين نفسي. Do you have it down there? Mine is down.
Yours is the same? The same theory. Score.
Where did it go?
Start at 2 and finish at 9.
So let me just go back.
Okay, so members, I think for you, you're already having this table.
And I want to have select that one. What should I do now? So that's the last one.
Okay, so the table we are having here is giving us the regression statistical summary, which now that's how we actually insert regression statistics in Excel.
Excuse me,
Yes.
maybe before we go far, I wanted to confirm.
Hey.
Are we supposed to get the same figures, for example, like on Marco R?
Because if we are basing on the same data, then possibly the figures should be the same.
No,
Unless there is a column or row you have left aside.
I don't know why main is different and I'm using the same.
Yeah.
Sure.
Yes. Even mine.
Because if we can redo it, but I'm seeing the figures are different. Mine.
Yours are also different.
You ask Mary, what is the figure?
Mine are the same.
Mary,
Like yours.
regression, how much is there? The figures of regression.
مبارك عندك نفس الحاجات معانا يا زلمة.
لأنه ما
كيف الفرق وين؟
Mary, what is your what is your R square?
total في شنو؟
2, 7, 9, 0.
R square is 0.
3 minus 3 6 9.
0.993391.
How many observations do you have?
How many what?
Observations. Like how many items did you select to include in your
How
data?
many people?
Under observations. Here.
Under observations, let me see. Under observations, I have 9. I think that's why.
Yeah. You left out one figure, one observation. So in
What are the
selecting
observations here?
observations mean these, how many are they from top to bottom? From when you count this 1, 2, 3 up to 10. So there are 10
So
observations.
were we also supposed to include? Were we also supposed to include the age, what, then the blood pressure?
Yeah, the
Those
3
ones.
of them. That means
Are we supposed to include them?
Yes.
Oh, that's what I left out.
Okay.
Let me run it again.
So you are going to pay for disturbance fees.
I accept.
Okay.
معانا سوا صح؟ ايوه قلت لك واحد نسيته.
Okay. So this data is now here with us. So what we are left with is now the interpretation of this data. Okay. Remember that we are having risk scores. So we are having risk scores, these risk scores here. We are running regressions to see what is the effect of all these three on risk scores. Like that, all these other three depend on risk scores. So we are seeing which of these is contributing to the risk scores. Okay, risk scores are already there. So we are saying that when we are running multiple regressions here, the maximum multiple regression value you can ever get is 1. Okay, is 1. That's because these are interpreted as probabilities. The maximum probability for any observation is 1. So we are asking these are the ranges of interpreting multiple regression, multiple R. If R is between 0.0000 up to some zeros, many zeros, meaning not when I say 1, but it is between 0.00 up to 0.044. We say we interpret that data that is it is a weak positive correlation. We say, let me make sure that this one, okay, weak positive. I want the reader to see it. A weak positive correlation. Now, these are standard values which you use to make decisions on whether R is weak, is strong, or very strong. So the value of R here, for you to interpret, you must have these interpretation guidelines. There are guidelines for interpreting R. If it is between 0.045 to 0.69, is it 0.4? Let me use 0. This is 0.4. This is 0.69. So then this one is also 0. That like that. We say that this is a moderate positive correlation. Moderate positive correlation. But again, when it shoots 0.7 up to 0.8, others take it 0.84, like that. Some this one we say it is a strong positive correlation. Strong but positive. If it is 0.5 up to 1, then we say that is very strong. very strong positive correlation. Remember that multiple R means Pearson correlation coefficient. So Pearson correlation coefficient tells us how strong is it, how strong is one variable in relation to those that are affecting it. So here we are saying that what is the effect of these age, blood pressure, and cholesterol on risk scores? On risk scores, it is observable that the risk scores here are at 0. Sorry, this multiple regression R is at 0.98, which lies in our what? We can now create that and that, compare that with that. It falls in the range of very strong positive correlation. The same R regression can also be negative, but when it is in the direction of negative, like here you have negative 0 point something, and they are negatives, and all these are negative values. These are negative. For example, if it was negative 9.8, we would still also say it is very strong negative, because it is a two-way direction. It is either positive or negative. But the one we are having now is a what? Is a positive. So that's where it lies. It is harder for a student or a researcher to interpret multiple regression if the researcher does not have these ranges of interpreting the multiple regressions.
Excuse me, Wilber.
Yes.
I was inquiring now for us do the risk scores. Assuming I do 0.01 to 0.44 without adding all other 3 zeros, will it be different?
Like that.
Yeah.
It is okay.
Yeah.
It is okay. That's okay.
Okay. Okay.
Mm.
Of course, yeah.
Mm.
There was so many zeros that confuse people.
Okay.
Yeah.
These are t values, p values.
So,
Yes.
if someone were going to evaluate multiple F, or evaluate what?
Sorry.
Someone were going to evaluate tuition value. Here. The multiple F is very strong, isn't it?
Yes. That is very strong.
Yeah, all of it
Positive.
very strong, just like standard.
Now, multiple, what we call R square. We have here R square. Okay. R square is used to measure what percentage do the independent variables contribute to the dependent variable. What influence do they have on the dependent variable?
Okay.
What effect does age, blood pressure, and cholesterol level have on the risk scores. This one is telling us that it is 96.5%. R square is translated into percentages in interpretation.
It's very strong.
Yeah, because now this one I just want to make it a percentage and make it percent. You see, it's 96.5%.
Very strong.
Yeah, that means it is also, usually they are moving together. If the other one is very strong positive, this one also tells you that the effect in percentage is also larger. Now from there,
The standard error, that's mean it's a week. Isn't it?
sorry.
The standard error
Mm.
is 5 point something. That's mean under the moderate positive correlation.
Yes, yes.
Okay.
Now, when it comes to interpretation of p-values, what are p-values? Okay. P-values here. Now, these are the specific significance levels for each of these variables. They are also called levels of significance for each of these variables. For age, it has 0.09. For blood pressure, 0.3. Cholesterol has 0.3 also, like that. So here we are having p-value of 0.95. The interpretation of p-values is based on the standard error, or what we called the 5%. This 5% here, which is 0.5% is what?
But the best is maybe the crystal.
Out of 100, right?
0.05.
So 5% is 0.05.
Yes.
Now this one, the 5%, we are getting it from the other confidence level. Remember, we set the confidence level to be 95%. So we were 5% expecting the error. So anything that lies within 0.05 is significant. And anything that goes beyond 0.5 is, we say it is insignificant. Why? Because by going beyond 0.5, the error will be so big that we lose confidence in that data. This 0.05, which we are also calling the standard error we set, is also called the alpha value. Alpha value. So when you hear alpha value, at what level did you set your alpha value? Is almost the person is asking you, what error did you expect? Because that varies depending on the researcher. So you cannot interpret these facts here unless you have declared the alpha value, that your alpha value is 0.5, 0.05. Therefore, this value here is insignificant, is not significant because it is higher than the alpha value. P-values, for them to be significant, should be less than 0.05. So here we say that specifically if you were to look at only age and seeing how age actually contributes to the risk scores, it is telling us that it will be 95%. It is 9.5%. Okay, 9.6,
Because yes, I have some figures there.
which is slightly higher than the set alpha value 0.05. So meaning that this age does not
Insignificant.
yes, it is not significant, does not contribute to the risk score. What of that? Blood pressure. Even blood pressure is at 30.5%, far above the set alpha value of 0.05, and even cholesterol levels. Now we can see here, for example, this one is at age 55 with a score of 7. This one is at, is it? Yeah, this is blood pressure. Okay, this is not age. Age is here. 58, 7. Want to get a number close to 58, which is 68. Yeah. So we can see yes, age positively, but this positively, yes, contributing to that, but the contribution is really very, very small. So we cannot consider it to be very significant.
Wilber,
Yes,
just go back to that table.
here.
It's as if the risk score, which for me feels like it's significantly, affecting the risk score. Because if you look at 63 there, it's 9. 58, it's 7. 60, it's 8. 52, it's 6. So it's as if the higher the age, the higher the risk score, which seems like it's significantly, affecting the risk score.
You know what we call significance? Is sorry, when we what you call significant, the p-value, this p-value should be less than the alpha value. You know what we call significance in real life is like some students in your school score the highest scoring 60, and the others following that person scoring 58, 57. You say that really the difference is really not significant, but would be alarming if one scored 60 and others are scoring 20. Then you will say, I'm going to put more efforts to help somebody because the difference is very significant.
Okay.
So though they are, this statistics is showing us that they are contributing, but it is not, if you looked at only age, true, it is contributing, yeah, up to 9.5. Which one would say yes, the contribution is there, but because it is less than the error you've set, the alpha value, so it is higher, yeah, higher than the alpha value, then you say it is not significant because you've set the parameters which you should follow to consider what is significant and what is not significant.
Okay.
Yes. Okay. Now we also have here the coefficients. These coefficients tell us that if, for example, we wanted to know each individual, because I think here we are not having the standard deviation, we didn't add, we didn't run with the descriptives here, so we don't have the descriptives with us, but age is measured in years. Which years is 1, 2, 3, huh? So you measure age by years in terms of 1, 2, 3 age. You measure age in terms of years which are 1, like that, in that order. Then cholesterol levels, you are also measuring them by pressure. Pressure, 1 millimeter of mercury, like 1 Pascal, yeah? So 1 millimeter of mercury, you're also measuring it by 1, 2, 3, 4. Even cholesterol levels, these are magnesium per decimal liter. You're also measuring them one by one. It tells us here that for you to interpret these coefficients, you use, because this one we are calling it regression analysis, but you're actually regressing what you a line, eh? would be drawing a line, like a line. So that's why we call them linear regressions. Linear from the word line. So possibly someone to interpret this properly would have the mind of a straight line. These are actually coefficients. These coefficients mean if there is, for example, age, if one age changes 1 year, a person increases by 1 year, what would the risk score be? Usually these values should not exceed the risk scores. If a person increased by 1 year, 1 year, then the risk scores, what would be the risk scores? This tells us that let me try to do this. We have to have an equation here, which trying to type an equation here is something. I want to say x1 to mean alpha naught, which is this. I'll put this, I'll put that to mean alpha naught.
This is X0.
Otherwise, I would have used the word alpha. Yeah, let me use alpha so that X is reserved for alpha naught plus, and these are equations, plus another alpha, which we mean this coefficient, plus this is plus beta 1 beta x. This is beta 1x. I just need to make these ones to be
D1
is what we call
should be like a D1.
we call them subscripts. Yeah? How do you insert subscripts in Excel? Anyway, let's consider them to be subscripts, plus beta 1x. This is beta 1x plus beta 2x. How many variables are we having? This one will stand for age. This other one, beta 2, will stand for blood pressure. Then we are remaining with what? With the 1 for cholesterol level, which is beta 3. This is the equation that interprets our data. For example, following these coefficients, we can be able to predict a person who is aged 35, what risk scores that person could really do what could really have. Using this equation, we say alpha, which is 10, alpha naught. Alpha naught means this general coefficient. If we go to that one plus beta 1, which is for age, times what is the x, the person who is aged 35. The person who is aged 35 plus this person who is aged 35 but has pressure of that is another b. That is this is now another. Let's put another beta. This one beta 2 for blood pressure times, if that person had this blood pressure, we want to predict risk score, plus, and the person also had cholesterol, which is beta 3, then times the one who is having this cholesterol of 175. What would that be? You see this one, you see this risk score, it is 1.83. Almost, if we took this to be to 0 decimal places, to be 2, meaning that if the person is aged 35, would have the risk score 2. You get it? Basing on the equation, these coefficients which are guiding this. Let me try to go to another one, aged 58. Basing on the translation, this one is shifting from up. it is shifting our alpha. If we went to predict, I just want to maintain these ones not to change, the beta values, these ones not to change. I want to lock them off. That's the first one, that is alpha naught. But let the other ones on top change. Okay, this one is, I'm locking these cells with the dollar sign so that they don't change at all. I'm looking the wrong one. I'm looking the wrong one. I'm supposed to lock this. That's the second beta, right? Then I'm supposed also to lock this one. So what I want is these coefficients not to change, but the edge to change, to see what we are predicting. So if we were to drop a little down, you see this?
Yeah.
For age 58, we predict that that person will have 7. But let me raise a little up. Raise a little up, and say we'll raise a little up. You can see that the figures remain the same, contributing that, okay, if this is this, the same is this almost equal to that, we'll say false because this was decimal places. But the other one is already programmed to be to nothing like a decimal place at all. But these decimal places are there in the background because they are real calculated values from these other decimal places. So that's how we predict a dependent variable from independent variables, given that we have been able to identify the equations. The equations.
Excuse me, Will.
Yes.
I don't know if the team is equation here. So this one, is it a fixed formula of A0 plus B1x?
It being a fixed formula, right?
Yes, that's what I'm asking.
Yeah, that is the formula for interpreting the coefficients. It depends on how many variables are you having in your table. If, for example, we had another variable which, maybe someone in medics, if it is not blood pressure, then it is ulcers. And it's the fourth to be our B4, then X not, then X for it. So it continues depending on how many are variables.
A0 stands for what?
A0 stands for that is the intercept, which is for all the y-intercept.
Okay.
You see, we are following a line which is equal to y is equal to, this is a straight line, mx plus c, plus c. You remember that line in school?
Yes.
That is the line of this. That is a straight line, right? That is a straight line.
Yes.
An equation of a straight line where m is equal to the gradient. And then c would be equal to the y-intercept. You see that? But for us here, we are saying our y, if we want to predict, is we want to predict risk score. So that is the y. So here we were even supposed to put y is equal to this equation here. I would even put it here. Y is equal to that equation. But in statistics here, we are saying here that C in research, you can call it, other people call it beta naught, beta zero, where x values are not there. That is the intercept. Y-intercept means that that's the point where x values are not there at all. It is only y values. That is why for it here, when we were stating it, we were just putting it direct there. We didn't multiply it with anything because x is not there. 0, there is no other variable apart from the predictor variable, the dependent variable. So we usually call it alpha naught. Other researchers call it beta naught. But it is the y-intercept. A position on the y-axis where the line, this line, touches the y-axis. Usually at that point where the line touches the y-axis, x values are not there at all. So these variables, when these variables are not there at all, that's where we say that will be the y-intercept. Then this beta 1, this one, is the gradient for the line for edge. Because for us instead of saying mx, we are saying beta 1x, which beta 1 here is the gradient of the line for edge. So actually this one, edge, we are calling it beta 1. I will put that. Then this one, we are calling it beta 2. Then this one, we are calling it beta 3. Beta 3. Then how they keep changing? They keep changing depending on the value which we want to predict. So for that, that's how we interpret this data for now. So thank you for this. I would like to first close this one here. This DF stands for degree of freedom. degree of freedom. Usually to get degree of freedom, we get uh, we get our values, those which is the formula for degree of freedom is n df equals n minus 2, like that, where n is the sample size,
N,
n minus 2,
N minus 2, that's mean.
where n is the sample size, which is 10. Is the sample size, which is 10.
That's,
Usually degree of freedom,
it is a rule. That's a rule, right?
yes,
Okay. Yeah, it's innovation.
you remove a pair
No, okay.
from the samples,
DF, okay.
from the samples. But this can be very good if it were using SPSS. So the
Okay.
next time we shall
We shall use
we
SPSS.
shall use SPSS to
To find, because actually,
To interpret.
yeah
they said
to
this one's regressions.
to
And let me do
interpret
that.
this. So members, that's how we compute this. I would like to thank you for being there, and also I'm here with Mr. Mubarak, Madam Rehab, Mr. Ali, Madam Mariam has also been with us, Madam Catherine. Now online we have Ali going on still, is online, Madam Scovia among, Mr. Richard. This is Mr. Ronald Ahirira. So thank you. And even Mary Kawajungu. Madam Mary, how are you? Okay. Has this
I'm
been
okay with that.
okay. Has this been helpful?
Has been of help. That
Okay.
is very true.
Thank you.
You're welcome.